Have you ever really stopped to think about how a machine actually learns to translate languages? I mean, it's not magic, right? It all starts with one absolutely crucial first step, teaching the computer how to read. So today, we're going to break down how we turn our human language into something a machine can finally understand.
So what's the fundamental problem we're trying to solve here? Well, a computer doesn't get what hungry means, or soccer, or love. Deep down, it only speaks one language, and that language is numbers. So our job is to become the ultimate translator between our words and its numbers. And this slide right here just nails the whole challenge. On the left, you've got a simple, everyday phrase, I'm hungry. But on the right, that's what the machine actually sees, just a sequence of numbers, what we call a vector. The big question is, how in the world do we get from one to the other? Well, let's get into it.
Okay, so first things first, we have to create a dictionary. You can really think of this like a Rosetta Stone for the machine. We're going to give every single word a unique numerical code that it can actually process.
But before we can even build that dictionary, we need to do something called tokenization. Now, it sounds fancy, but it's a really simple idea. We just take a sentence and break it down into its individual parts, or tokens, which for us are basically the words. This is step one for bringing some order to the chaos of human language. Once we have all our tokens, we can build this, a word-to-index map. It's exactly what it sounds like. Every unique word gets its very own number. I'm becomes 4, hungry is 5, and so on for thousands of words. You'll also notice we have these special tokens, like pad for padding and EOS for end of sequence. These are going to be super important for helping the machine understand the structure of our sentences, as you'll see in just a minute. And, this has to be a two-way street, right? After the machine does all its number crunching and makes a prediction, we need a way to turn its numerical answer back into words we can actually read. And that's exactly what this index-to-word dictionary is for. It's the key that lets us understand the final translation.
So, we've got our dictionary. Now what? Well, this next part is kind of like following a recipe. A recipe for turning any sentence you can think of into a perfect, machine-ready list of numbers.
And it's a super simple three-step recipe. First, we tokenize the sentence, swapping each word for its number from the dictionary. Second, we tack on a special marker at the end to say, hey, the sentence is over. And third, we pad the sequence with zeros to make sure everything is the same uniform length. Let's see how it works.
Okay, let's take our simple example, I'm hungry, and run it through our three-step process.
First up, tokenization. We look up I'm in our dictionary, boom, it's number 4. We look up hungry, and that's number 5. Simple as that. We've officially turned the words into their core numerical forms. Now, for a really critical step, we have to tell the machine exactly where the sentence stops. We do that by adding our special end-of-sequence token, the EOS token, which we assigned to the number 1. This little marker is so important because it prevents the machine from just reading on forever and getting totally lost.
And our final step is padding. So why do we do this? Well, you can think of it like this. Machine learning models are a bit picky. They need all their data to fit into perfectly identical boxes. So we figure out what the longest sentence in our entire dataset is, and then we just add zeros, or pad, all the shortest sentences until they're all the exact same length. These zeros are just placeholders, but they create that uniform structure the machine needs.
And just like that, our data prep is done. We've successfully taken messy, raw sentences and transformed them into this beautifully structured dataset, all formatted perfectly for a machine translation model to start learning from.
And here it is, the grand finale. We've got our language pair, English and French. On the left, you see the original text, and on the right, their final form. These clean numerical vectors, all the exact same length, complete with that EOS token and the padding. This is the kind of data our model can actually work with. So let's just quickly recap the 3 big ideas here. 1, every single word gets turned into a unique number. 2, every sentence gets a clear stop sign with that EOS token. And 3, every single sentence vector is padded so they are all a uniform length. That structure, it's everything. And this whole process isn't just a nice to have. It's the absolute starting line. The source material puts it perfectly. Given that you know how to represent words, you can go ahead and start training your model. This structured data is the foundation that everything else is built on.
So, we've done it. We've turned our words into numbers. The data's prepped, it's clean, it's ready to go. But this brings us to the next and maybe even more amazing question. How does a machine take these long lists of numbers and actually learn the patterns, the grammar, and all the nuance of human language to pull off a translation? Well, that's a story for another time.